Recording's rolling. It is Monday, September 22nd. So we're taking today the next 2 days. So 3 day block fair to do these two labs. As you guys were walking in class, hand you guys this page. Has a couple of Atwoods on one side and well, it says friction lab on the other side. You said each of these has two halves to it. There's the friction labs and two halves, and the Atwood labs also in two halves. So it's sort of like four mini labs, right? Yeah, I think 3 days is perfect to pace this out over here. And I'll show you guys how this goes here. Don't worry about the thing that says AP because that's extra. All right. I do want to mention before I get going too far, I did last week hand you guys these puzzles, but I want to solve a lot of these puzzles in class Thursday. That's my plan, and see how it paces out. These are not going to be due for almost a couple of weeks. So Friday, October 3rd, which is not this Friday, it'd be the following Friday. Right? Yeah, so I've been planning this out for the weekend, and yeah, again, I think there'll be probably plenty of time in class where I can do probably most of these with the guys in class. So you guys do have the homework puzzles, but yeah, if you read them, that could only help you. All right, so what's going on with these labs here? Maybe I'll start with the friction side since I've got this here. All right, so there's a question you're trying to answer, and actually I did write, I did spell it out on a page that might be within reach because I have this out for my AP students. Okay? I guess the question up here says, what's the coefficient of kinetic friction between, say, like two surfaces? Right? And I actually have it twice because there's two completely different methods to hone in on the same answer. It turns out that one method you only need spring scales as a measuring tool, and the other method, strangely enough, you could actually determine the answer to this question with nothing but a protractor. I'll show you guys sort of how to do that and see how much you guys can figure out. So you guys remember last week, we're talking about dynamics forces, and one force that pops up is this friction force. Okay, so actually, this picture right here, this setup is one of the setups for your labs today. Okay, so this is the see, you guys see this one on the left side says what's the weight, what's the pulling force, what's the coefficient of friction, or there's a graph here. Okay, so this right here. Now, what you can do is you can take different lab weights. You guys have, of course, box of lab weights, lots of different lab weights here. You can lift the lab weights with a spring scale, and I'll tell you the weight. So 200 grams weighs, I should say right here, yeah, 2 newtons. You guys see 2 newtons right there? Is this 200 grams? Okay? So you can record that. But guys, if this block, suppose that's this right here. Guys, if this weighs 0.2 newtons, isn't that mg, is gravity force, 2 newtons? Right? What support force from the table? With a horizontal table. This is a horizontal table. Right? What's the normal force right here? That would also be 2 newtons, wouldn't it? You guys see that? Right? And then there could be some applied force which can read directly off the spring scale. So if I'm trying to drag this across the table, it would actually look a lot like this, wouldn't it? Okay, so I'm just trying to drag it at constant velocity, and that's an important aspect too. Because guys, think back to last week. If an object has constant velocity, what is its acceleration? Zero. Zero acceleration. If there's zero acceleration, then what is the net force on the object? Zero. Also zero. Yeah, 0 newtons. Yeah. Which means that the free body diagram would look like that. You guys remember what a free body diagram? It shows all the forces on it. So this right here, right, is that dragging horizontally across the paper, has 4 forces on it, and it looks just like this. Okay, so yeah, you have the weight down, maybe 2 newtons, for example. You have the normal force holding it, which would also be 2 newtons. Okay? Maybe I'm applying with whatever the spring force is. Suppose it said 1 newton. I'm just making something up. Suppose it said 1 newton. What would the friction force also have to be?
2.
What 1 newton, right? Yeah. Yeah, because if this is 1 newton and this is 1 newton, see how they're canceling out horizontally, right? Yeah, okay, all right. It's it, right? All right. Which means that whatever the spring scale is showing also represents the friction force. Right? Hey guys, if you know the friction force and you know the normal force, because this is 1 newton and this is 2 newtons, could you solve for this coefficient of friction right here, the mu k? Right? Just this 1 divided by this 2, and that would be 0.5, wouldn't it? Right? No, I just made up those numbers. I don't know if that's exactly what you're going to get, but that could be a plausible, realistic answer. Yes, that. Okay. Now, can you do that for lots of different lab weights? So could you change out and have lots of different lab weights so you can measure newtons? Lots of pulling forces across the horizontal surface, measure that. And then, could you graph that? Now, this graph actually says the pulling force versus the weight. There's like direct readings. Okay. But guys, if it's constant velocity, wouldn't it's not blurry. Come on, focus here. Okay. Wouldn't the pulling force be equivalent to the friction force in magnitude, and the weight would be equivalent to the normal force for that particular setup? Okay. So if you thought about it that way, that would end up being the same graph. Can you guys label your vertical axis or horizontal axis, plots and points. I wonder what shape curve is going to look like. There's a couple of questions down here, and it hones in on you're trying to figure out what's the coefficient of kinetic friction. Okay? What's that sort of like that friction factor as you're sliding? You guys get that? Okay. Now there is a completely different way to also get the same coefficient, right? And I'll show it to you here. It's this poster. Now, this one's a lot more involved, but you can have an incline. Actually, I see some tracks in the back that are already inclined. You guys see that already inclined? Okay. Okay. Now, this one, you want to say stack a weight right here, right? And then lift this to some angle. You guys got some protractors back there, or some protractors. Okay. Until this naturally slides down at constant velocity. Again, constant velocity. That means the net force is what? Zero. Yeah. And back on Friday, the very last thing, I got it in just before the bell on Friday. Do you guys remember? You drew this in your notes? Remember that? It's the last thing in your notes. I got it in. Right. Okay. And there's how many proper forces are on this block right here? 3. Okay. The weight pulls straight down to the center of the earth. The normal force points, guys, it's straight up. No. You're right. It is not. It's perpendicular to the surface, isn't it? That's what normal, right? Perpendicular. Right? And then you guys see how the friction is like parallel to the surface? Is that right? Now, if I take the weight and I split it into components that are, again, aligned with the surface, we get a nice little right triangle looking shape right here. Okay? Okay. Guys, what is this normal force equivalent to in terms of the weight? Cosine. The cosine component. Guys, if this is 29 degrees, is this 29 degrees? It would be the same angle, right? Right, okay. So you can kind of see that visually. Right. So this normal force is equivalent to mg cosine theta. So if you have like a 10-degree angle, here, let me see what cosine of 10 degrees is. Cosine of 10 degrees would be, for example, 0.98, right? That's like 98%, right? So this would be a little less than the actual weight, maybe 98% of its weight, something like that. Right? As the angle goes up, that changes more. Right? But this friction force, and you know there's a friction force because it has to cancel out this component mg sine theta, so that to put it in equilibrium. That's this right here, right? Well, oops, I gave away the question I was going to ask. I was going to say what's this equivalent to, but you guys would have said anyway. Mg sine theta, right? Isn't the friction force and the mg sine theta the same? Is that right? Now, I have a whole derivation proof here, and this poster's on my wall. It's over there. You guys see it's over there, so you can reference it if you need to. Right? But there's this whole thought process goes like this. Well, constant velocity means zero acceleration. Zero acceleration means zero net force. Right? And then I can look along each axis and figure out what does that mean along each axis. So along the, I'll call this the x-axis. This friction force and this mg sine theta, these two guys have to zero out, which means that they're the same magnitude. That's this line that brings us to this line right here. Okay? But the friction force, see if I go back to this one, guys, what's the friction force equivalent to? Coefficient of friction times the normal force. And if the question is what's the coefficient of friction, now you have a way to solve that starting with this line right here. Yes, it's the same thing, right? These are all the same thing. It's just one line at a time, right? Right. But the normal force is equivalent to what? Mg cosine theta, right? I know it's a lot of little steps, right? What I'm trying to show you guys is how you can get the coefficient of friction with nothing but a protractor. Okay? And this very last step right here is what cancels out on both sides. The what and the what? Does the m cancel? And also the g, right? Now, maybe I'm giving away too much because ideally maybe solve this for yourself from scratch, or you figure it out from scratch just by doing the experiment. But sort of giving you a heads up how this is, at least ideally, supposed to turn out, how it's turning out today, right? Which is, I'm making the claim, and you guys can test this to see if it's true, right? That maybe it doesn't matter what mass you have, right? And it doesn't matter what gravity field for that matter. So I think you would get the same result on the moon. Like if this is sliding down at constant velocity, I'll just make something up. Suppose it's like 11 degrees on Earth. Would it still be sliding down constant velocity at 11 degrees on the moon? According to what I say here, I'm saying that's going to be the case. Right. So then, back to your paper. Can you guys pick different weights? You guys got a whole box of lab weights here. Well, I'm pulling a lot of them out, but I say, pick different ones and see what angle does it slide down. Now, if you're really comparing apples to apples, you guys know that this coefficient of friction is a material property. So strictly speaking, you would want to have the same materials, which if one of these is painted in like black paint, that is different than bare metal. So a little different. Okay. Actually, earlier, so my AP class, what they did is they took masking tape. They wrapped masking tape around so they could control from materials they had. What would the masking tape against that metal crack back there be? And then they could solve it that way. All right. So you guys ready to move over to Atwood? All right. So I'll have some Atwood posters. Actually, let me put these to this. Well, actually, this is a really good picture right here. So the idea is you're taking one of these pulleys right here, hold this black bar vertical, put a string through. Now the string you want to be probably about a meter long. Can you guys do that? About a meter long string. Okay. And then take a couple of lab weights. They put one here and one here. Right, hook them to the string and then let it go. Okay. Now, is this going to accelerate because there's some kind of net force going on? Accelerate, do you think? Okay. Then how much would it accelerate? What if I do this? What if I replace this guy with this guy? Ah, it's going to accelerate more. Great. What about this? What if these two lab weights are the same? Actually, I bet you guys could figure this one out even before trying it out. Guys, if this is 200 grams, and this is 200 grams, and you let it go, what's this whole system do? Yeah, no, it just sits there, sits at rest. Oh, okay, that might give you a hint as to how this might work. Or at least this would be a boundary condition, wouldn't it? Right? Right. So, okay, so I know whatever I think the answer is, right? And the question is, how is this going to accelerate as a function of the masses? I know that whatever answer I come up with, if the masses are the same, it should result in zero acceleration. That would make sense, right? What about this? What if I take this guy off and I just have weight on one side and an empty string on the other side, and then I let it go? How much would you expect this to accelerate straight down? The full rate of gravity, the full like 9.8 meters per second squared. That would be the opposite boundary condition, wouldn't it? Okay, so again, that's another hint as to maybe a bigger picture how this could work. Right? When I eventually debrief this with you guys, I'll start doing second law of motion and show you guys exactly how this works. Right? But here's maybe what might end up being the answer. The acceleration is something. It's some function of these masses in 1 and in 2. You guys get that? Okay. So what does that look like on your lab table? Right, so on the opposite side here, I have a classic Atwood here, and I have, later on we'll get to what's called a modified Atwood. So let's start with the classic Atwood, because that's the picture I was showing you. Right? Again, this string is maybe like a meter long, so this is really a cartoony version. But what are you recording across the top here? Right, so you got different trials going on. Let me unblur this. Okay. G is 980 centimeters per second squared. What is that? Where'd that come from? 980 centimeters per second squared. Is that pure free fall?
Yeah.
Yeah, in terms of centimeters, it is. Yeah, sure. All right. Can you record M1 and M2? And you can vary these throughout the lab. So, yeah, you can swap them up. But what I might recommend too is, guys, what do you think is easier to time with the stopwatch? Where they're very similar in mass and it accelerates very slowly, or they're very different mass and it just plummets to the ground? Probably very similar. Could you do this? Could you attach 200 grams on one side, 200 on the other, and then maybe tag on a little tiny mass on additional one side? Right. So yeah. Right. So just to weigh one side a little bit differently than the other. So this should accelerate slowly, which is easier to use the stopwatch. Right. So what else we got going on? Right, so you got two different masses. Now I'm telling you here, take the difference in masses and the sum of masses. Right? The difference I put absolute value bars on because I don't really care if it's going clockwise or counterclockwise. Okay. X. Guys, what do you think X in centimeters represents? How what? Yeah, how far apart they started, right? How far they moved, right? In some time interval, because the next column is t in seconds. So suppose you start them like 100 centimeters apart, which is probably recommendable, right? So they switch places. So 3, 2, 1, go. Right? And they will be accelerating. Right? There will be some kind of force. And can one of you control a stopwatch and say start, stop, and get how many seconds that takes? Right? Can you guys do 3 and take an average? It's probably good practice too, right? Okay. And then at this point, it's like the right 4 columns are all sort of kinematic. Right? You guys remember kinematic days, right? Those 3 kinematic equations and so on. Right? You can calculate the acceleration because look at this. Start from rest. It goes so far in centimeters and so much time on the stopwatch. Isn't that 3 kinematic variables? So in principle, you can calculate acceleration. In fact, I can tell you exactly how to do it. I'm really, really helping you guys out here. You guys remember that college equation right there? X equals 1 half AT squared? Remember that? Okay. So if you rearrange that, you can solve for acceleration and show you exactly how to do that. Okay. If you have a question about that, let me know. I'll be walking around helping you guys out, of course. Right? But the question everything's leading up to is this question right at the bottom. Can you find a relationship for, say, an expression? Right? What is the acceleration of the system, say like downward acceleration of large mass, for example, as a function of the masses and Earth gravity? And I starred 4 of these columns. You guys see some asterisks right here? So Earth gravity starred because that does matter. Right? If this was on the moon, I think it would move a little different, right? The sum of the masses, the difference of the masses, well, the difference, the sum, right? And then your calculated acceleration going through kinematic motion, right? Which is kind of like the y value here, right? Like acceleration equals something. Right? There's some way you can multiply and divide these first 3 columns that should land you pretty close numerically to that fourth column. Okay, you guys get that? Yeah. Okay. And then last part, let me swap up my posters here. Okay, is what's sometimes called a modified Atwood. Modified Atwood. Now this one, I still got two masses, M1 and M2. But guys, which one of these masses does the weight cancel out? Is the weight canceled out? How about this M2? Okay, you see it's canceled out by this normal force? Is that right? No, the M1 is hanging. Now, of course, there's this resistive tension force on M1, although from a system point of view, it's just holding the system together. So you don't have to find the tension of the strain or anything. Like maybe later on in the week we will, but not for this lab. Okay? But you guys see here, oh, I put little wheels here. So I have this low friction cart. Can you guys hear the wheel spinning? Right, very low friction. And there's a low friction track right there. These will fit right into the grooves. Right, so this, but I should give it a tiny push and this thing will roll. Right, look at that. Right, it just rolls, right? Okay. Now, guys, take a guess. What do you think is more massive? This empty cart or this 500 grain mass? What do you think is more massive? 500. Turns out they're the same. Yeah. Turns out they're the same. Right. This is 500 grams. But if you want to test that for sure, there is a triple beam balance in the back of the room. You can put this on triple beam balance and get upside down. It'll come up 500 grams. Okay. Could you stack more weights on it if you wanted to increase the mass? Can you do that? Right. Yeah. So you're allowed to do that. Right. In fact, you probably want to vary something. Right. Right. So here's your setup. Now, this could fall some distance. There's some meter six back there. So it might be like, oh, I don't know, maybe 80 centimeters, whatever the height of the table is, or something like that. Okay? And you can, again, time it with the stopwatch, say how much time does it take to fall? And then from that, you can record this on the table. Let's go to this table right here. Okay? Right, so you're recording what is M1 and M2, what is masses. Right, what's the sum of the masses ends up entering into the answer. Right, how far did it fall, x in centimeters? Take 3 times in an average with the stopwatch. You can calculate the acceleration. Again, going through kinematic motion. Right, you guys good so far? Right. And then at the bottom, I did star some of these columns again. Again, the table looks a little different than the left side of the paper. And there's some expression. What is the acceleration as a function of the masses? Right, guys good? Okay. Right, so recap everything we're doing. We're taking these 3 days, Monday through Wednesday, to do these 2 labs that each have 2 halves to them. Okay. One of them is a friction lab where you are pulling horizontally with constant velocity, and you can record numbers and make a graph. Another one is, this one's a little bit more involved conceptually, right, where you can tilt some surface until it slides down at constant velocity. You can use a protractor to measure that angle. There's a way you can find coefficient of friction that way. There's this classic Atwood where you hang them both vertically. Sometimes I call this a double elevator, right? Maybe different masses and time, how far it takes to move. You can calculate acceleration that way. Okay. And then there's this modified Atwood where you have that low friction cart rolling horizontally. Right? So it has inertia, it has mass. It's going to slow down the system for that reason, right? But its weight is actually canceled out by its normal force. Right? And so what's the acceleration of the system if the masses are arranged like that? Right? So that's your questions. You guys got 3 days, and then turn this lab in at the end of Wednesday. Again, don't worry about anything that says AP. Okay. Yeah, we'll get to textbook puzzles later this week. All right, everything you need is back in the lab area. I will walk around and help you guys out.